In this presentation, we're going to look at the binomial distribution and using the normal distribution to approximate the binomial distribution. Usually what happens in the start of these questions, there's usually some sort of theory definition about the central limit theorem, also known as the CLT. Anyway, first off, let's look at the question. Over the years, it's been observed that of all undergraduate students in mathematics who take a societies exam, only 57% pass. Suppose that this year, 950 graduate students in mathematics are taking the examination. What is the probability that more than 565 pass? That's the first question. And then between 535 and 575 passing. Okay, so in this case, what we have to do is sort of just actually define what our variable here, x. X is number passing, okay? Just make a little statement like that. Okay, I didn't really do it here below, but I really should have. Okay, our little sentence about it, number of students who pass the exam. Okay, and we can say that x is a binomial variable, binomial, with 950 n and 0.57 as p. Okay, going out a shot there, very close to it. So what we can do here is approximate this using the normal distribution. Okay, so mu and sigma squared. Okay, essentially calculations on this basis will be fairly tricky, but calculations on this basis should be fairly manageable. Okay, so that's the idea. We use the normal approximation to normal distribution to approximate the binomial distribution, just to make life simple. Okay, now based on the central limit theorem, we can approximate the binomial distribution using the normal distribution. Usually some sort of justification is required with all of these approximation questions. In the first instance, usually it's a sample size is important. In other cases, you might be able to show that the mean is greater than a certain value, n times p is greater than 5 or something like that. So we'll work on the basis for this instance that we have a large sample size of 950. Okay, so just be prepared to justify it. So what we have to do here is calculate the mean and the variance. Oops, didn't mean to do that. Mean and variance is of the binomial distribution. So, and these are calculations you should know, definitions you should know. N times p gives us the mean for the binomial distribution. 950 times 0.57. The mean is 541.5. The variance is 950 times 0.57 times 0.43, and that gives us 232.845. Okay. Just to be clear, Q is 1 minus P, which is 1 minus 0.57. Okay. Now, what we're going to do is we have our variance here. Okay, but what we really need is our standard deviation there, which is the square root of 232.845. It is 15.2593. Okay, so essentially what we're able to do here is put in those values there. So you can just write in mu is equal to 541.5 and sigma squared is equal to 15.2593 squared. I don't really have space there, but it just sort of fill that out a little bit. Okay, so again, sigma squared equals 15.29 or 2593 squared. Okay, because we're going to be using 15.2593 in our calculations, we can just leave it, express it like that rather than 232.845, because we'll be using 15.2593 very soon. Now, this is important as well. Correction factors. So we are working on the binomial distribution is a discrete distribution, and what we're going to be doing there is approximating it with a normal or a continuous distribution. So what we should do in this case is put in correction factors. Okay, now, so what we will be working with is this one here. So it's more than 565. Okay, probably x greater than 565. So when we get our normal, when we use our normal distribution we'll just replace 565 with 565.5. Okay. Now x less than or equal to n. So we're going to be using this here in this question here. I'll come back to this one shortly, actually. Okay, we'll just start off with the first one. So probability of x greater than 565. So what we're going to get here is the z-score. So this is binomial, and this is the normal side over here. Okay, and essentially what I'm going to do is just go straight into finding the z-score. Okay, so that's the z-score that we're working with there, z-score. Okay, that is x, whatever our value of x is, that we adjust it here, minus mu over sigma. Okay, that's what's going on there. So the little asterisk there is just to sort of say that we've added in the 0.5 here. We've put in that adjustment, that correction factor there. Okay, but essentially it's a z-score. This is a straightforward normal distribution question now. So you should be familiar with the normal distribution before you attempt stuff like this. But essentially this is just calculate the z-score and then work out the probability, the corresponding probability. That's 0.0583. Okay, so that's the answer to the first one. So I just moved over to the second one here. Now, this part B. Now, the thing is we have 535 less than x and x less than or equal to 575. So essentially you just notice we do two slightly opposite things here. So that is minus 0.5 and that is plus 0.5 to our values. This is binomial over here and this is normal. Binomial, and this is the normal side over here. Okay, so let's just scroll up just to double check that. So there's two, I've sort of tidied that up a little bit. So we're using that one in one instance and that one in the other instance. Okay, so in the second instance, or this is the 535 one, that becomes 534.5. And x less than or equal to 575, that means 575 becomes 575.5. Okay, I paused there for a second because my pen started slipping, but I'm back on track there. So sorry, now something I was going to say here is the probability of x less than or equal to n could just make it a little bit clearer, just re-express it as follows there. Okay, so that's when we are looking at our interval. So let's go back down. Okay, so we can split our interval into two and get the z-score of each. Okay, so we have this part here, that's the z-score. Okay, and essentially when we work it out, this is actually very straightforward normal distribution calculations, which hopefully you should be fairly okay with now at this stage. So the z-score for the first component there, 534.5, that should equate to a z-score of minus 0.46. 575.5, that should equate to a z-score of 2.23. So essentially what we are dealing with is an interval of minus 0.46 to 2.23, which is a standard normal distribution. So essentially what we should be looking at here is just, you can sort of split this up a little bit here. Okay, make it two intervals, a combination of two intervals, and then just apply the complement rule just to make it a little bit easier. But at this stage this is using the tables. Okay, so you should be getting an answer of close to 0.6643. Okay, so that's it there.